Welcome to my channel. In today's live, we will be reading chapter 8, Force and Pressure. This is the chapter of NCRT CBSE board. I'm just checking the alignment and then we will start it. I hope the screen is clear to everybody. The alignment is correct now. The text is visible. Let's begin. So this is chapter 8, Force and Pressure of class 8th science. In case you are interested in hearing the audio of first 7 chapters, they are there in the playlist with the name Audiobook Class 8 Science. You can come to the playlist of my channel Online Biology Tutorials and there you will get it. In class 7, you have learned how objects move. Do you recall how we can decide whether an object is moving faster than the other? What does the distance moved by an object in unit time indicate? You also know that a moving object like a ball rolling on the ground slows down. Sometimes it may change its direction of motion. It is also possible that the ball may slow down and also change its direction. Have you ever wondered what makes an object slows down or go faster? Or change its direction of motion. Let us recall some of our everyday experiences. What do you do to make a football move? What do you do to make a moving ball move faster? How does a goalkeeper stop a ball? A hockey player changes the direction of the moving ball with a flick of the stick. How do fielders stop a ball hit by a batsman? Figure 8.1. In all these situations, the ball is either made to move faster or slower, or its directions of motion is changed. We often say that a force has been applied on a ball when it is kicked, pushed, thrown, or flicked. What is a force? What can it do to bodies on which it is applied? We shall seek answers to such questions in this chapter. 8.1 Force, a push or a pull. Actions like picking, opening, shutting, kicking, hitting, lifting, flicking, pushing, pulling are often used to describe certain tasks. Each of these actions usually results in some kind of change in the state of motion of an object. Can these terms be replaced with one or more terms? Let us find out. So, this is the activity 8.1. Table 8.1 gives some examples of familiar situations involving motion of objects. You can add more such situations or replace those given here. Try to identify action involved in each case as a push or a pull and record your observations. One example has been given to help you. So there are various actions given like moving a book placed on the table. It is pushing, it is pulling, it is lifting. You need to find it out. An action can be grouped as a push or a pull, or it is both. So similarly, you need to find for opening or shutting a door, drawing a bucket of water from a well, a football player taking a penalty kick, a cricket ball hit by a batsman, moving a loaded cart, opening a drawer. Decide now. Do you notice that each of the actions can be grouped as a push or a pull or both? Can we infer from this that to move an object it has to be pushed or pulled? In science, a push or a pull or an object is called a force. Thus, we can say that motion imparted to objects was due to the action of a force. When does a force come into play? Let us find out. I learned in class 6 that a magnet attracts a piece of iron towards it. Is attraction also a pull? What about repulsion between similar poles of two magnets? Is it a push or a pull? Now to this side. I hope the page is completely visible to everybody. Let's move ahead. 8.2 Forces are due to an interaction. Suppose a man is standing behind a stationary car as shown in A. Will the car move due to his presence? Suppose the man now begins to push the car as here. That is, he applies a force on it. The car may begin to move in the direction of the applied force. Note that the man has to push the car to make it move. Figure 8.3 shows three situations that may be familiar to you. Can you decide who is pulling and who is pushing in these cases? In figure 8.3a, both the girls appear to push each other, while the pair of girls in figure 8.3b are trying to pull each other. Similarly, the cow and the man in figure 8.3c, this one, appear to pull each other. The girls in the two situations shown here are applying force on each other. Is it also true for the man and the cow? From these examples, we can infer that at least two objects must interact for a force to come into play. Does an interaction of one object with another object results in a force between the two objects? Now the next page. 8.3 Exploring Forces. Let us try to learn about forces. Activity 8.2 Choose a heavy object like a table or a box, which you can move only by pushing hard. Try to push in all it all by yourself. Can you move it? Now ask one of your friends to help you in pushing it in the same direction as shown in figure 8.4a. Is it easier to move it now? Can you explain why? Now push the same object but ask your friend to push it from the opposite side as seen in B. Does the object move? If it does, note the direction in which it moves. Can you guess which one of you is applying a larger force? Have you ever seen a game of tug of war? In this game, two teams pull at a rope in opposite directions. Figure 8.5 Members of both the teams try to pull rope in their direction. Sometimes the rope simply does not move. Is it not similar to the situation shown in figure 8.3b? The team that pulls harder, that is, applies a larger force, finally wins the game. What do these examples suggest about the nature of the force? Forces applied on an object in the same direction add to one another. Now recall what happened when you and your friend pushed the heavy box in the same direction in activity 8.2. If the two forces act in the opposite directions on an object, the net force acting on it is the difference between the two forces. What did you observe in activity 8.2 when both of you are pushing heavy box from opposite directions? Recall that in the tug of war, when two teams pull equally hard, the rope does not move in any direction. So, we learn that a force could be larger or smaller than the other or equal to each other. The strength of a force is usually expressed by its magnitude. We have also to specify the direction in which a force acts. Also, if the direction or the magnitude of the applied force changes, its effect also changes. Does it mean that the net force on an object is zero if the two forces acting on it in opposite directions are equal? Next page. In general, more than one force may be acting on an object. However, the effect on the object is due to the net force acting on it. 8.4 A force can change the state of motion. Let us now find out what happens when a force acts on an object. Activity 8.3 Take a rubber ball and place it on the level surface, such as a tabletop or a concrete floor. Now, gently push the ball along the level surface. Figure 8.6 Does the ball begin to move? Push the ball again while it is still moving. Is there any change in its speed? Does it increase or decrease? Next, place your palm in front of the moving ball. Remove your palm as soon as the moving ball touches it. Does your palm apply a force on the ball? What happens to the speed of the ball now? Does it increase or decrease? What would happen if you let your palm hold the moving ball? You might recall similar situations, for example, while taking a penalty kick in football. The player applies a force on the ball. Before being hit, the ball was at rest and so its speed was zero. The applied force makes the ball move towards the goal. Suppose the goalkeeper dives or jumps up to save the goal. By his action, the goalkeeper tries to apply a force on the moving ball. The force applied by him can stop or deflect the ball, saving a goal being scored. If the goalkeeper succeeds in stopping the ball, its speed decreases to zero. These observations suggest that a force applied on an object may change its speed. If the force applied on the object is in the same direction of its motion, the speed of the object increases. If the force is applied in the direction opposite to the direction of motion, then it results in a decrease in the speed of the object. I have seen children competing with one another in a moving rubber tire or a ring by pushing it. Figure 8.7. I now understand why the speed of the tire increases when it is pushed. Next page. Paheli is curious to know whether application of a force can only change the speed of an object. Let us find out. Activity 8.4. Take a ball and place it on the level surface as you did it in activity 8.3. Make the ball move by giving it a push. Now place a ruler in its path as shown in figure 8.8b. In doing so, you would apply a force on the moving ball. Does the ball continue to move in the same direction after it strikes the ruler? Repeat the activity and try to obstruct the moving ball by placing the ruler in such a way that it makes different angles to its path. In each case, note your observations about the direction of motion and the ball after it strikes the ruler. Let us consider some more examples. In a game of volleyball, players often push the moving ball to their team mates to make a winning move. Sometimes the ball is returned to the other side of the court by pushing or smashing it. In cricket, a batsman plays, hits, or her shot by applying a force on the ball with the bat. Is there any change in the direction of motion of the ball is in these cases? In all these examples, the speed and the direction of the moving ball change due to the application of the force. Can you give few more examples of this kind? A change in either the speed of an object or its direction of motion or both is described as a change in its state of motion. Thus, a force may bring a change in the state of motion of an object. State of motion. The state of motion of an object is described by its speed and the direction of motion. The state of rest is considered to be the state of zero speed. An object may be at rest or in motion, both are its states of motion. Does it mean that the application of a force would always result in a change in the state of motion of the object? Let us find out. It is common experience that many a time application of force does not result in a change in the state of motion. For example, a heavy box may not move at all even if you apply the maximum force that you can exert. Again, no effect of force is observed when you try to push a wall. 8.5. Force can change the shape of an object. Activity 8.5. Some situations have been seen in column 1, table 8.2, in which objects are not free to move. Column 2 of the table suggests the manner in which force can be applied on each object, with column 3 shows a diagram of the action. Try to observe the effect of force in as many situations as possible. You can also add similar situations using available material from your environment. Note your observations in column 4 and 5 of the table. So, studying the effect of force on objects, description of the situation, a lump of dough on a plate has been kept. How to apply force, pressing it down with your hand. So, this is the diagram. You need to write whether there is a change in a state of motion or change in shape. Similarly, you need to fine for other cases. Spring fixed to the seat of a bicycle by sitting on the seat. A rubber band suspended from a hook nail fixed on a wall by hanging a weight or by pulling its free end. A plastic or metal scale placed between two bricks by putting a weight at the center of the scale. Next page. What do you conclude from the observations noted in table 8.2? What happens when you apply a force on the inflated balloon by pressing it between two palms? What happens to the shape of a ball of a dough when it is rolled to make a chapati? What happens when you press a rubber ball placed on a table? In all these examples, you saw that the application of force on an object may change its shape. Having performed all the above activities, you would have realized that a force may make an object move from rest, may change the speed of an object if it is moving, may change the direction of motion of an object, may bring about a change in the shape of an object, may cause some or all of these effects. While a force may cause one or more of these effects, it is important to remember that none of these actions can take place without the action of a force. Thus, an object cannot move by itself, it cannot change speed by itself, it cannot change direction by itself, and its shape cannot change by itself. 8.6 Contact forces. Muscular force. Can you push or lift a book lying on a table without touching it? Can you lift a bucket of water without holding it? Generally, to apply a force on an object, your body has to be in contact with the object. The contact may also be with the help of a stick or a piece of rope. When we push an object like a school bag or lift a bucket of water, where does the force come from? This force is caused by the action of muscles in our body. The force resulting due to the action of muscles is known as muscular force. The viewers who are connected with me, in case you are liking the audio or the pronunciation of the video, please hit the like button and share it with your friends. Consider subscribing in case you are interested in hearing the audio of further more chapters. So, whenever live will be scheduled, a notification will definitely reach you. It is a muscular force that enables us to perform all activities involving movement or bending of our body. In class 7, you have learned that in the process of digestion and the food gets pushed through the alimentary canal, could it be a muscular force that does it? You also know that lungs expand and contract while we inhale or exhale air during breathing. Where are these muscles located which make breathing possible? Can you list a few more examples of the force exerted by the muscles in our body? Animals also make use of muscular force to carry out their physical activities and other tasks. Animals like bullocks, horses, donkeys, and camels are used to perform various tasks for us. In performing these tasks, they use muscular force. So, similarly, this has been shown to you in figure 8.9. Next page. Since muscular force can be applied only when it is in contact with an object, it is also called contact force. Are there other types of contact forces? Let us find out. Friction. Recall some of your experiences. A ball rolling around along the ground gradually slows down and finally comes to rest. When we stop pedaling a bicycle, it is gradually slows down and finally comes to a stop. A car or a scooter also comes to rest once its engine is switched off. Similarly, a boat comes to rest if we stop rowing it. Can you add some more such experiences? In all these situations, no force appears to be acting on the objects, yet their speed gradually decreases and they come to rest after some time. What causes a change in their state or motion? Could some force be acting on them? Can you guess the direction in which the force must be acting in each case? The force responsible for changing the state of motion of objects in all these examples is the force of friction. It is the force of friction between the surface of the ball and the ground that brings the moving ball to rest. Similarly, friction between water and the boat brings it to a stop once you stop rowing. The force of friction always acts on all the moving objects and its direction is always opposite to the direction of motion. Since the force of friction arises due to contact between surfaces, it is also an example of a contact force. You will learn about you will learn more about this force in chapter 9. You may be wondering whether it is essential for the agent applying a force on an object to be always in contact with it. Let us find out. 8.7 Non contact forces, magnetic forces. Activity 8.6 Take a pair of bar magnets, place the longer side of one of the magnets over three round shaped pencils or wooden rollers as shown in figure 8.10. Now bring one end of the other magnet near the end of the magnet placed on the rollers. Make sure that the two magnets do not touch each other. Observe what happens next. Bring the other end of the magnet near the same end of the magnet placed on the rollers as seen in figure 8.10. Note what happens to the magnet placed on the rollers every time another magnet is brought near it. Next page. Does the magnet on the rollers begin to move when the other magnet is brought near it? Does it always move in the direction of the approaching magnet? What do these observations suggest? Does it mean that some force must be acting between the two magnets? You have learnt in class 6 that like poles of two magnets repel each other and unlike poles attract each other. Attraction or repulsion between objects can also be seen as another form of pull or push. Do you have to bring the magnets in contact for observing the force between them? A magnet can exert a force on another magnet without being in contact with it. The force exerted by a magnet is an example of non contact force. Similarly, the force exerted by a magnet on a piece of iron is also a non contact force. Activity 8.7 Electrostatic force. Take a plastic straw and cut it into nearly two equal pieces. Suspend one of the pieces from the edge of a table with the help of a piece of thread as shown in figure 8.11. Now hold the other piece of straw in your hand and rub its free end with a sheet of paper. Bring the rubbed end of the straw near the suspended straw. Make sure that the two pieces do not touch each other. What do you observe? Next, rub the free end of the suspended piece of straw with a sheet of paper. Again, bring the piece of straw that was rubbed earlier with paper near the free end of the suspended straw. What do you observe now? A straw is said to have acquired electrostatic charge after it has been rubbed with a sheet of paper. Such a straw is an example of a charged body. The force exerted by a charged body on another charged or uncharged body is known as electrostatic force. This force comes into play even when the bodies are not in contact. The electrostatic force, therefore, is another example of a non contact force. You will learn more about electric charges in chapter 12. Gravitational force. You know that a coin or a pen falls to the ground when it spills off your hand. Leaves and fruits also fall to the ground when they get detached from the plant. Have you ever wondered why it is so? When the coin is held in your hand, it is at rest. As soon as it is released, it begins to move downwards. It is clear that a state of motion of the coin undergoes a change. Can this happen without a force acting on it? Which is this force? Next page. Objects or things fall towards the earth because it pulls down. This force is called force of gravity or just gravity. This is an attractive force. The force of gravity acts on all the objects. The force of gravity acts on all of us the time without our being aware of it. Water begins to flow towards the ground as soon as we open the tap. Water in rivers flows downwards due to the force of gravity. Gravity is not a property of the Earth alone. In fact, every object in the universe, whether small or large, exerts a force on every other object. This force is known as gravitational force. 8.8 Pressure. Is there a relation between pressure and force? Let us find out. Try to push a nail into a wooden plank by its head. Did you succeed? Try now to push the nail by a pointed end. Figure 8.12. Could you do this time? Try cutting vegetables with a blunt knife and then with a sharp knife. Which is easier? Do you get the feeling that the area over which the force is applied, for example, the pointed end of the nail, plays a role in making these tasks easier? The force acting on an unit area of a surface is called pressure. Pressure is equals to force on an area on which it acts. At this stage, we consider only those forces which act perpendicular to the surface on which the pressure is to be computed. I now understand why porters place a round piece of cloth on their head when they have to carry heavy loads. By doing this, they increase the area of contact of the load with their head. So the pressure on their head is reduced and they find it easier to carry the load. So we are still left with 4 pages. Stay connected. We will be finishing it soon. Note that the area is in the denominator in the above expression. So the smaller the area, the larger the pressure on a surface of the same force. The area of the pointed end of the nail is much smaller than that of its head. The same force, therefore, produces a pressure sufficient to push the pointed end of the nail into the wooden plank. Can you explain now why shoulder bags are provided with broad straps and not thin straps? And why the tools meant for cutting and piercing always have sharp edges? Do liquids and gases also exert pressure? Does it also depend on the area on which the force act? Let us find out. 8.9 Pressure exerted by liquid and gases. Activity 8.8. Take a transparent glass tube or a plastic pipe. The length of the pipe tube should be about 25 centimeter and its diameter should be 5 to 7.5 centimeter. Also take a piece of thin sheet of a good quality rubber, say a rubber balloon. Stretch the rubber sheet tightly over one end of the pipe. Hold the pipe at the middle, keeping it in a vertical position as shown in 8.1 for this one. Ask one of your friends to pour some water in the pipe. Does the rubber sheet bulge out? Note also the height of the water column in the pipe. Pour some more water. Observe again the bulge in the rubber sheet and the height of the water column in the pipe. Repeat this process a few more times. Can you see any relation between the amount of the bulge in the rubber sheet and the sheet of the water column in the pipe? Activity 8.9. So, whatever description they have written here, the image is given here. Take a plastic bottle. You can take a discarded water or soft drink bottle. Fix a cylindrical glass tube a few centimeters long near its bottom as shown in figure 8.15. You can do so by slightly heating one end of the glass tube and then quickly inserting it near the bottom of the bottle. Make sure that the water does not leak from the joint. If there is any leakage, seal it with molten wax. Cover the mouth of the glass tube with a thin rubber sheet as you did in activity 8.8. Now fill the bottle up to half with water. What do you observe? Why does the rubber sheet fixed to the glass tube bulge this time? Pour some more water in the bottle. Is there any change in the bulge of the rubber sheet? Note that the rubber sheet has been fixed on the side of the container and not at the bottom. Does the bulging of the rubber sheet in this case indicate what water exerts pressure on the sides of the container as well? Let us investigate further. Activity 8.10. The students who are connected with me since beginning, thank you for being connected till now. In case you are interested in hearing the audio of first 7 chapters, you can visit the playlist. You can consider subscribing to have the recent notifications. Take an empty plastic bottle or a cylindrical container. You can take a used tin can or a used plastic bottle. Drill 4 holes all around near the bottom of the bottle. Make sure that the holes are in the same height from the bottom. Now fill the bottom with water. What do you observe? Do the different streams of water coming out of the holes at the same distance from the bottle? What does this indicate? Can you now say that liquids exert pressure on the walls of the container? Do gases also exert pressure? Do they also exert pressure on the walls of their containers? Let us find out. I have seen fountains of water coming out of the leaking joints or holes in pipes supplying water. Is it not due to the pressure exerted by water on the walls of the pipes? When you inflate a balloon, why do you have to close its mouth? What happens when you open the mouth of an inflated balloon? Suppose you have a balloon which has holes. Would you be able to inflate it? Can we say that air exerts pressure in all the directions? Do you recall what happens to the air in the bicycle tube when it has a puncture? Do these observations suggest that air exerts pressure on the inner walls of an inflated balloon or a tube? So we find that gases too exert pressure on the walls of the container. 8.10 atmospheric pressure. Do you know that there is air all around us? This envelope of air is known as atmosphere. The atmospheric air extends up to many kilometers above the surface of the earth. The pressure exerted by this air is called atmospheric pressure. We know that the pressure is force per unit area. If we imagine a unit area and a very long cylinder standing on it filled with air, then the force of gravity on the air in this cylinder is the atmospheric pressure. Figure 8.17. But how large or small is the atmospheric pressure? Let us get an idea about its magnitude. Activity 8.11. Take a good quality rubber sucker. It looks like a small rubber cup. Press it hard on the smooth plain surface. Does it stick on the surface? Now try to pull it off the surface. Can you do it? When you press the sucker, most of the air between the cup and the surface escapes out. The sucker sticks to the surface because the pressure of the atmosphere acts on it. To pull the sucker off the surface, the applied force should be large enough to overcome the atmospheric pressure. This activity might give you an idea about the magnitude of atmospheric pressure. In fact, it would be possible for any human being to pull the surf sucker off the surface if there were no air at all between the sucker and the surface. Does it give you an idea how large the atmospheric pressure is? If the area of my head were 15 by 15 centimeter, how much force air will exert on my head? The force due to air in a column of the height of the atmosphere in area 15 by 15 is nearly equal to the force of gravity on an object of mass 225 kg. The reason we are not crushed under this force of gravity is that the pressure inside our bodies is also equal to the atmospheric pressure and the balances the pressure from outside. Did you know Otto von Guericke, a German scientist of the 17th century, invented a pump to extract air out of a vessel. With the help of this pump, he demonstrated dramatically the force of the air pressure. He joined the two hollow metallic hemispheres of 51 centimeter diameter each and pumped air out of it. Then he employed 8 horses on each hemisphere to pull them apart, as shown in figure 8.20. So great is the force of air pressure, then the hemispheres could not be pulled apart. With this, we are done with the reading of this chapter. The keywords used in this chapter are atmospheric pressure, contact force, electrostatic force, force, friction, gravitational force, gravity, magnetic force, muscular force, non contact force, pressure, pull, push. Summary of the chapter. Force could be push or a pull. A force arises due to the interaction between two objects. Force has magnitude as well as direction. A change in the speed of an object or the direction of the motion or both implies a change in its state of motion. Force acting on an object may cause a change in its state of motion or a change in its shape. A force can act on an object with or without being in contact with it. Force per unit area is called pressure. Liquids and gases exert pressure on the walls of their containers. The pressure exerted by air around us is known as atmospheric pressure. So, with this, we are done with the reading of a lengthy chapter in life. That was chapter 8, Force and Pressure. In case you have listened it completely till now, thanks a lot. Stay connected, consider subscribing so that you can get the recent notifications. In case you are interested in hearing the audio for 7 chapters, a playlist has already been uploaded on my channel. Thank you. See you in next video.